Okay, we'll wrap up this section looking at number 31. Again, we're looking at evaluating definite integrals of shapes that have known geometric formulas. And in problem 31, we have the integral from -3 to 3 of the square root of 9 minus x squared. Now this is a form that you should get used to recognizing. It happens to be a semicircle, and it started with a circle centered at the origin with radius 3. And that would have given you a formula x squared plus y squared equals 9. When we solve that for y, you first get y squared equals 9 minus x squared, and then, taking the square root, you would have y equals plus or minus the square root of 9 minus x squared. So only the positive one of those would be the upper semicircle of that circle. So again, it's a circle centered at the origin, radius 3, and the area between the curve and the x-axis then would just be the half of the area of a circle with radius 3. And so, in this case, the area will be 1/2 pi r squared, where r is 3, so it's 1/2 of 9 pi, or 9 pi over 2. And that does it for problem 31. I'll quickly review the graphing calculator usage, and you should be able to get that. So I want the square root of 9 minus x squared. I'm going to go ahead and graph that. And second trace, option 7, lower limit -3, upper limit 3, and we get a value of 14.137929. Now you should know that when I hit the store button, well, I won't go into that. And it gives you the answer there. The answer, that value is stored in the answer variable, and we can go out and actually print that out. So it's 14.137. If we wanted to see that that's equal to 9 pi divided by 2, we get the same exact thing. Slightly different because of rounding errors, finding the area using the integration techniques that are there. So once again, if I wanted to do this using the math key, math, fnint, vars, yvars, function, y1, comma, the variable of integration, then the lower limit, comma, the upper limit, and we get the same exact thing. Right? So each one of those is slightly different, but that's because of the techniques that are used in each case are different, and we're going to get some rounding areas when we're doing the integration using numerical methods. Right? But that should do it for this particular type of problem.